Hello. I will remind you a little bit what we have accomplished last Sunday. So we calculated, first of all, we calculated several things. One of the things that we managed to calculate is this formula for the average energy. Okay. Now, first of all, what we are looking on. So it's a problem of a black body radiation. Okay, so the assumption is that we have a black body. All right, which is empty inside, and we have some sort of radiative waves that are standing inside this cavity. We assume that those waves, okay, are in complete equilibrium with the body itself. So all the electromagnetic waves that are absorbed by the walls of this body, nothing is reflected, and after a while also electromagnetic waves are emitted by the same walls. They are in total equilibrium. We looked on this problem as a standing wave problem. We calculated the partition function. Okay. In the first place, all the photons now were independent. There were no limitations on the maximal frequency that can be achieved, for this system, and eventually we obtain an expression for the energy. Right? This expression was an integral from 0 to infinity, epsilon. We had here v divided by pi squared c h bar to the third. You all have this in your notebooks. Epsilon squared e beta epsilon minus 1 d epsilon. And then what we claimed is that this guy over here is simply the probability density function of the energy. Okay? The probability to observe a radiation inside this cavity, inside the black body, with energy epsilon. So this is probability, energy probability density. Energy probability, this is a probability density function. Density function. Okay. What it means, if I want to calculate what is the probability to observe energy epsilon, this is simply this guy v divided by pi squared c h bar to the third epsilon squared e beta epsilon minus 1 d epsilon. Okay. And this is, in some sense, the answer to our original question. What was our original question? Is how can we make this transition from looking on light, looking on a spectrum of colors of the lights that we absorb in our equipment, and the relation to the temperature of the body that's emitted this light. Okay? And this is exactly this guy, because what we do in every experiment, optics experiment, okay? So let's assume that we have a camera or a CCD, whatever. We absorb different photons, and we can decompose all the different photons according to the energy of each photon that we absorb, okay? Or groups of photons. Okay? So here we can have a histogram of obtained energies. And here the x-axis will be energies. Okay. And we can, well, I can look on this chair, for example, absorb all the energy, all the photons that are coming to my camera from this chair, okay? And then I build a histogram of all the different energies of my photons that were emitted by this chair, okay? And that usually will look something like this, okay? There is a peak, so usually small energies are not there. There are very, very large energies are also not there. And there are some maximal energy which corresponds usually to the color, okay, to the color of the surface, right? So in this case, it's something like purple, right? And so this is Emax, okay? So I can obtain those results from experimental observations. What this formula that's written over here allows us to do, it allows us to perform some sort of a fit, okay? Some sort of a fit to the theory that, for example, this chair is approximately black body, right? It's definitely not, but we can assume that the light that is emitted from every chair or any surface is in some sense in equilibrium with the surface, okay? In equilibrium. So the radiation that's emitted, part of it is of course the reflective waves, but part of it is going to be the emitted waves, okay? And those emitted waves, we assume that they are in some sort of an equilibrium with the incoming waves. So we can try and plot this formula, okay? And it usually will show something like this, for example, right? So what we will usually see that there are some discrepancies between our theory, okay, which is the red line over here, and the experimental observations, which are those dots, that basically the histogram that we built. What it means that our theory is not perfect, but this is usually the case, okay? We need to perform some sort of a modifications, okay? We should assume that there is not a perfect equilibrium. We should assume that part of the radiation that we observe are not the emitted radiation, but reflected radiation, right? Et cetera, et cetera, et cetera. But for the first order approximation, it's good enough. Why it's good enough? Because, well, I can take this formula and say where the maxima, this Emax, is located, okay? So in order to achieve this, I need to solve an equation which is d to d epsilon of v divided by pi squared c h bar to the third of epsilon squared e beta epsilon minus 1, okay, equals 0. Which basically means that, well, we don't care about the constants. Okay, so we have 2 epsilon divided by e beta epsilon minus 1 plus epsilon squared divided by e to the power beta epsilon minus 1 multiplied by minus 1 e to the power beta epsilon multiplied by beta. Okay? All of this equals to 0. And what epsilon is this? This is epsilon max. Max, 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 and max. Okay? So you see, the only constant, the only parameter in this equation which determines what is the maximal energy of my theory is this beta. Okay? I don't have any other parameters. I have Emax and beta. Yep.
One of the
Squared. Thank you. Yeah. Okay. So the maximal is solely dependent on beta. What is beta? 1 over k Boltzmann T. So if I have a specific temperature, if I have a maxima and I fitted somehow my theory, although it's not perfect, I have some sort of approximation for the temperature of the object, that the light of this object I was absorbing in my experiment. Now, this I can move forward and say, well, I can measure the temperature of the sun. I will absorb all the spectrum, or the light that's coming from the sun. I build this histogram. I'll fit it to my theory. Okay, I will find the epsilon max. Okay, and this is how I will know what my temperature is. Okay, I can build thermal cameras based on this guy. Okay, for measuring temperatures, what is hidden inside walls. I can do a lot of different and cool stuff. Okay, so but it's a crude approximation. We can say it's a first order approximation to measuring temperature from distances, but it actually works. Okay, you can say, well, Stas, how you can observe, okay, how you can absorb energy, because you were assuming that all this radiation is actually located inside, okay, inside your black body. Well, usually what people do, it's also in laser physics, but also in a lot of constructions that is done for nuclear physics, they assume that they have this cavity, and some of the light is emitted from small hole. So if you have this assumption, or your system looks like a cavity with a small hole from which some of the radiation is emitted outside, okay, this works actually pretty well, right? Because you still have this radiation that's located inside the cavity. It is still in equilibrium, and you're observing only the stuff that it's getting out, and it hasn't been shifted into some other frequencies by anything that happens between the emission and the absorption of your experiment. Why it still works for chairs, people, to some extent? Well, as I told you, I can assume that at least part of the radiation that's coming out from my body is in some sort of equilibrium with my environment. This equilibrium is not really good, but it's semi-equilibrium, I can say. This is why the theory is not good for regular objects. But stuff like sun, different suns, the approximation is pretty good. I think the last sentence that I mentioned on Sunday, was cosmic background radiation. Yep.
So you have one energy related to one temperature, the temperature of the body.
Yes.
So you're basically saying the other energies are the effect of the
No, there are many energies. This is not what I'm saying. I'm saying that there are coming huge number of different photons that are emitted from my body. They have a distribution of energies. Okay? My goal is to collect all those energies and plot a histogram. Okay? I'm collecting all the energies. I'm performing a spectral decomposition. Right? And I'm saying I have 10 photons that had very low energies, 20 photons that had higher energies, 1,000 photons that had a specific energy Emax, and less photons that had energies that are higher than Emax. I can plot this histogram, and I'm saying, well, what is the temperature of this body that emitted this light? And then I'm using my theory that I just erased, this theory over here. Okay, so I'm not saying that all my photons have a very specific energy. I'm saying they have a distribution, but the only thing that I'm fitting is the maxima over here. And in order to fit the maxima, I need to solve this equation. Okay? And I have only one parameter, beta. Fine? Further questions? No. So we mentioned cosmic background radiation. So cosmic background radiation, we're not going to solve anything related to this thing. It's just a story. Cosmic background radiation. But this is a very nice story. CMB. Cosmic CBR. Cosmic microwave background. Cosmic, I know the name is different. Microwave background. CMB, right. So CMB has a very nice story. So in 1964, there were two astrophysicists, astronomers by the names of Penzias and Wilson. So they had a radio antenna, and they were exploring some sources and that are coming from outer space, basically collecting electromagnetic radiation, okay, and trying to find specific stars, emitting stars. The stars sometimes emit at different frequencies, not only light, but also microwaves, radio waves, etc., etc. And they had some problems. What kind of problems usually experimentalists have? They have noise, right? So if you try to perform any experiment, you will see that there is a lot of noise coming from all different sources around you. And the main part of your time as experimentalist you will be doing by somehow just keep this noise far away from your system, at least for a while. Okay, now, those two guys had the antenna, radio antenna, and they had a noise which was pretty peculiar, have a specific frequency. Not one frequency, it was a distributed frequency. And the funny thing about it is that it was always, no matter where they pointed their antenna, they had the same noise that was affecting their results. So first of all, those two guys thought, well, probably the birds or pigeons. Okay, so they tried to keep away the pigeons, and they, built a big plastic net that also introduced some additional noise on top of their antenna. But they were trying to fight really, really hard to actually kill this noise, right? Now, after a while, they started to think, well, the problem was no matter where they pointed their antenna, no matter at what time of year they were pointing their antenna to different locations, so it's doesn't really matter where you're located with respect to the sun, okay, or to the moon, you still have the same amount of noise. It was coming from everywhere around them. Okay? Now they published the results, and they met a guy who was a theorist, and he told them about some predictions that were based on the Big Bang theory. Not the comedy movie, the actual theory. Okay. Now the Big Bang theory, it is spectacular theory, and it has several predictions. So how all this starts, there was a huge Big Bang, okay, VO, a lot of light. After a while, everything started to cool down, okay. So at some state, we have up to 380,000 years after the Big Bang. There's still almost everything is in a plasma state. What is a plasma state? So we have protons, we have electrons, but we don't have atoms. Okay? No atoms whatsoever. But everything cools down little by little because the universe is expanding. Okay? So this expansion causes a red shift, so everything cools down due to the expansion. Like an expansion of a gas. Okay? So everything cools down, and at some point, this 380,000 years after the Big Bang, this is what the theory says, the recombination event starts. What's a recombination event? Recombination event is that everything had become cool enough that it's preferable for the protons and the electrons to form the first atom. What is the first atom? Hydrogen atom, right? You solved it in quantum mechanics class, right? So the recombination event is then electrons and protons suddenly combine together, okay? And in order for the electron to get from the lowest energy to the next energy, or to just escape from this atom, one needs 13.6 electron volt of energy. Okay? Why this event is interesting or important from the standpoint of Big Bang theory and how it's related to this CMB, microwave radiation. So think about it, what happened before. We have plasma state. A lot of electrons, a lot of protons, just in this big space. Now, what is an electron? An electron doing something like that. It's emitting radiation, right? You have an oscillations of a charged particle, it emits radiation, so there are also radiative waves also in this space. What is a radiative wave? It's a photon. Now, they are in some sort of equilibrium because one particle emitted a photon, another particle absorbed the photon, then it's emitted it again, and this process goes and on and on and on. The space is huge, so we have some sort of equilibrium between the different electrons and the radiation. Okay, what happens when the recombination event occurs? Okay, so everything is cooled down, and you have electrons that prefer that a minute before or very short time before, were in equilibrium with all the radiation around them. Suddenly they are bound to the proton, and they're no longer electrons, they are hydrogens. Now, the energy at that state is much less than the ionization energy of the hydrogen atom. A hydrogen atom, the energy to get the electron out of the outside of the atom is 13.6 electron volt. The energy of this radiation can be calculated according to this energy is around 2.6 electron volt. So it's definitely not enough for those radiative waves to do anything with the electrons. Okay, what happens to a particle, okay, that absorbs radiation, and this radiation is not sufficient to pull it outside to the next quantum level? Nothing happens. Okay, so all those hydrogen atoms became opaque for the radiation that's outside. Okay, now this radiation has nothing to scatter from, nothing to interact with. So we have a lot of photons, a lot of radiation that's outside in the space that's basically almost do not interact with anything. Right? Now, it's supposedly everywhere inside our universe. Okay? Now, one can go and calculate what is the spectral decomposition of this cosmic microwave background. What I just told you, it's radiation that was in thermal equilibrium with something else. So there are no reflected waves, there are only absorbed and emitted waves. So it should be a perfect black body according to the theory that we have right now. Okay? Now I can go, and this is what those guys did, Penzias and Wilson. Okay? They went and measured the spectral decomposition of their noise that they were fighting so long to kick out of their experiment. And what they have found is that it's a perfect fit. Okay? So when you plot and you perform an experiment, you usually use error bars in order to describe how much error you have in your result. So the error bars were smaller than the printed width of the line, actually. So the data was perfect. Everything felt extremely well. Okay, so here I say, well, I don't have a perfect fit. Everything went extremely well. This is one of the proofs. There are two major proofs. Another thing is anisotropy of some other radiation. Okay, but this is one of the proofs why the Big Bang theory works, because it predicted. So the existence of this background radiation and recombination event was predicted around the 40s. Those guys had no idea about that when they measured everything that they wanted to measure, so something like 23 years afterwards, and they found it completely independently. So this is one of the two major proofs why the Big Bang theory actually been there. Okay, and it's actually was a pretty exciting event. All right, so this is the story of cosmic of CMB and the black body radiation. We are moving to the next chapter, which is classical density of states. Any questions about the CMB? Yes.
About the Big Bang theory, at first the electron and the proton.
They were basically almost not interacting.
Yes.
It's a plasma state.
Yes.
And it's a curse because they think about it that everything was extremely hot. Okay?
Yes, the entropy of this system decreased.
Eventually, because the temperature decreasing. Okay, so think about two particles. Okay, I have one particle and I have another particle. They are interacting. Okay, there are some electromagnetic forces between two of them. Now, there are specific bound states, because we have to treat this quantum mechanically. So there are specific bound states of the proton and the electron. This is the hydrogen atom. When the internal energy of the proton and the electron is too high, it's not going to be bound. That's it. Right? Because if you plot, you have two particles. Two-body problem, it's always a one-body problem. So and when you solve two-body, which has a proton and an electron, you're assuming, okay, that you have energies. So you have a E0, E1, E2, E3, etc., etc., etc. And the spectrum becomes denser and denser and denser and denser and denser. So they are interacting according to quantum mechanics, but they have temperature. What does mean temperature? Their average kinetic energy. Okay? So the average kinetic energy puts those two particles somewhere over here in the spectrum. They're not bound. You usually see, well, what is bound particle if it's in E1, E2, E3. So the level, the energetic level is not too high, because if it's too high, you are basically saying they're almost not interacting with each other. And this is what happens when your temperature is extremely high. And the theory assumes that everything was really hot. Okay? Classical density of states and the Gibbs paradox. It's not exactly a paradox, as we will see. We have 15 minutes. All right, so what is the classical density of states? We know so far, for this canonical representation, that the only thing that matters is that we will manage to calculate the partition function, right? We have z, right? We have sum of I, e minus beta ei. The moment that we manage to calculate this guy, okay, everything else is solvable. We can obtain the free energy, we can take derivatives from here till Tel Aviv, and we can calculate whatever we want. Everything is calculable the moment we know what this partition function for a given system is. Now, up to now, what we managed to solve are systems where we eventually represented the system in an independent fashion, where all the particles were independent. And we call this a factorization. Now, if you try to remember, when we obtain this guy, okay, we're said, well, the system has states. Okay? Now, states, what do I mean by state? So from quantum mechanical perspective, it's easy. There are states. States are discrete. We have, for example, energetic states of a hydrogen atom. We know that there are discrete spectrum of energies. So this is actually very easy from the quantum mechanical perspective to say, yes, the system have different states, different energies for each given state. But what happens from classical mechanical representation perspective? Okay? Now, we show what this partition function is. We use quantum mechanics. But actually, the partition function was originally written by Josiah Gibbs in 1875. Okay? He had no idea what quantum mechanics is. He had no idea who Planck is, and definitely not who Einstein is, because Einstein wasn't born yet. Not even Bohr. And he have written a function of a form of a partition function. Okay? So he proposed, based on some other problems that are related to the classical gas, okay, that there is something that he named partition function, the name came from there, that looks like 1 over h to the third, an integral, okay, several integrals of e minus beta. Here he put the Hamiltonian of the system, which is basically the energy of the system, okay, and the integration had to be performed according to all the coordinates of the system and all the momenta of the system. This was a proposition in 1875 by Josiah Gibbs for the partition function. So this is the classical form. This is the classical form of the partition function. Eventually, we know that we have to write it like this, but originally it was written in this form. He hypothesized, okay, based on some specific examples, that one needs to calculate this guy over here. What this 1 over h to the third? Gibbs had no idea. He said this is some sort of a constant, okay, that should be determined from experiment. It depends on the system, and it should be dependent on the experiment itself. What this formula actually means, okay? So remember, what is this integral? So we have integral over x, integral over y, integral over z, integral over px, py, and p dpz. Okay, so we have a 6-fold integration. What this formula actually means? So remember, if we have z, which is a sum over I, e minus beta I, ei, right? So e to the minus beta I is proportional probability of a system to be in state I. Okay? From this formula, what Gibbs hypothesized is that e to the minus beta, your energy, dx, dy, dz. Let's do it only for one-dimensional system. So we have only dx and dpx. It is the probability proportional to the probability of a system to be at coordinate x with momenta p of x. Now, if we will write our Hamiltonian, okay, as a p squared divided by 2m plus u of x, which is, this is our potential energy, this is our kinetic energy. So it is e to the z is an integral over x, an integral over p of x of e to the minus beta p squared divided by 2m plus u of x dx dpx. Now, ux can be very complicated. The kinetic energy, it's always like that. So we can actually perform this integration, right? An integration from minus infinity to infinity of e minus beta p squared divided by 2m of px, of dpx, equals to a square root of 2m pi divided by beta. Okay? So the partition function for one-dimensional system according to Gibbs z equals to an integral over x square root of 2m pi divided by beta 1 over h e minus beta u of x dx. So exactly as here we say e to the minus beta h dx dpx is the probability of a system to be in coordinate x with momenta px. From this formula what we know is that e to the minus beta ux is the proportional, okay, to the probability of a system to be at coordinate x. Okay. This is the classical probability, or more precisely probability density function that was derived by Gibbs in order to calculate if I have a potential, right? Let's assume that my potential u of x as a function of x looks like something like this, right? This is my potential. And I ask you, what is the probability to find the system here? And that's x, okay? Why I'm asking about the probability? Because assume what happens. I have a particle, I have a temperature, right? So the particle constantly wiggles, okay? It has also kinetic energy, right? The temperature means that it's heat all the time by its environment, okay? So it wiggles around. It has a potential energy. Okay, so it's not going as usually in classical physics what it says. Well, if you have a constant energy, right, your particle, the regular classical theory without temperature, you say I have a constant energy in my system, okay, and the particle is wandering from this side to the other side. Okay, this is something to solve in analytical mechanics or in physics 101, Newtonian mechanics. Nothing really happens. The particle constantly moves from one place to another, okay? And you can calculate the period of movement, etc., etc. In our case, there are no constant energy, okay? There is nothing like that. The particle can be anywhere inside the system. The only restriction is that, well, that this potential is a binding potential that we can have an equilibrium. So, but the moment we have an equilibrium, the particle can be here, here, there, or there at any point. What we usually will do, if we look on the particle as a function of time, okay, this is x, this is t. The particle is all over the place. This is how its motion looks like. It looks random and stochastic. Okay? And when I want to say, well, what is the probability to find particle at x over here? What I usually do, I can measure it. How I measure it? I'm looking on the trajectory, extremely long trajectory. I count all the times that the particle was at this specific x, divided by it by the total measurement time, and this is the probability. Gibbs says I have another measure. Okay? This is the classical Gibbs measure. How I can calculate what is the probability of the particle to be at this specific position, right? It is simply e to the minus beta u of x multiplied by some constant. Call it some c. Why c? Because it's a normalization constant that we can calculate what it is. Right? What we are looking on from this formula is that the lower the energy, the preferable the position is. Okay? The higher the energy, the less preferable the position is. This is what we obtained from Gibbs representation. It's exactly the same thing as we had in the quantum mechanical wave. Right? There was, what is the probability of a system to be in state I is proportional to e to the power minus beta EI. The higher EI, the lower e to the minus beta EI. Okay? And vice versa. Exactly over here, I have one-dimensional classical system. I want to calculate the probability to be at this x. It's simply e to the minus beta ux. Okay, this is great, but there are some problem. First of all, what we don't know is how it's related to this representation. Okay? It's absolutely not clear why and how Gibbs decided to write this formula. Second point is, well, there was a word that I written before that it's called a paradox. We will see that this Gibbs theory leads us to something very unnatural and unclear about the behavior of physical systems. Okay? We will see it not today because we actually have no time, but what we are going to see on Sunday is A, why this is wrong, B, how we can correct it, and see how it corresponds to the quantum mechanical representation that we have been looking on up to now. Okay? So all of this on Sunday. Thank you.